Hello out there, and welcome to our lesson on Venn diagrams and set operations. So most of you probably have some experience with Venn diagrams, and when I say Venn diagram, you're probably picturing this guy here. That is just one type of Venn diagram, but probably the most common. But what specifically is a Venn diagram? What's the purpose of even drawing that type of picture? What we're trying to do with the Venn diagram is create a visual representation of the relationship between sets, right? You have two sets of things. That's what the typical Venn diagram picture represents. The two circles in the picture represent your two sets. And then the fact that those two circles overlap is telling you that those two sets have some things in common. Now, it's not always the case that our sets have things in common. Sometimes they have everything in common, sometimes they have nothing in common. So we have different ways that we can draw the Venn diagram to represent those different relationships. Now, in the Venn diagram, we have a rectangle around the circles, and the rectangle is used to represent our universal set. So it's used to sort of contain everything that we're talking about for that particular picture. And then each circle inside of the rectangle represents a subset of that universal set. Okay? So, for example, let's say that our universal set is animals. So we build this rectangle just to enclose all of the animals that exist in the world. And then we have all kinds of different subsets of animals, but for this first example, we're going to call set A all of the dogs in the world, and we're going to call set B all of the cats in the world. Well, there are no dogs that are cats, there are no cats that are dogs. That means there's no overlap in those two sets. Now both of them belong to the animal set, so both of those circles would go in that rectangle, but there shouldn't be any overlap in the circles because there's nothing in common to those groups, okay, in terms of names. So we call these sets disjoint. Okay, sets can be disjoint, and if they're disjoint, that means they have no elements in common. So here, again, is our universal set of animals. So all the animals in the world inside this rectangle. And then here we have a subset of the animals that we call dogs. And then we have another subset of the animals that we call cats. So again, all the dogs in the animal box, all the cats in the animal box, but no cats are dogs, no dogs are cats. So there's no overlap in those two circles. Okay? So if you had like... just get some examples of what would go in these spaces. If I had like a, let's say a boxer, right? A boxer is a type of dog, would go in that circle. Or what kind of cats are there? I don't know, hairless cat? Okay, I don't know, I'm not a cat person. The only kind of cat I would approve of would be one without hair to make me sneeze. So a hairless cat goes in the cat circle. Anyway, what was something that would go outside of the two circles would be anything that's an animal that isn't a dog or a cat. So maybe you could put like a turtle, right? Would be an animal that isn't a dog or a cat, and that kind of animal would go outside of those circles. Okay, but they're disjoint. That means no elements in common. Okay, so sometimes they have nothing in common. Sometimes the sets have everything in common, and we would call these proper subsets. So with proper subsets, all of the elements of a set are part of a larger group. So we know a subset means we have a set that comes from another set, and if it's proper, that means that they aren't exactly the same. So that's what's happening in the next example. So our universal set is still all of the animals in the world. They're going to go in the box. And then we have set A as birds, all of the birds in the world. And then B would be parrots. Okay, so what's happening is the birds would be here, and the parrots would be here. Where the parrots, set B, is a proper subset of set A. That means all parrots are birds. So all parrots go in the bird circle. But there's that space in between the two circles to represent the birds that aren't parrots, right? So all parrots are birds, but not all birds are parrots. So obviously parrots go in the parrot circle, but what could be something that goes in here? I don't know, maybe a pigeon, right? A pigeon is a bird, but it isn't a parrot. And then outside of those circles, you have any animal that isn't a bird. So you could put like a cat or a dog or a turtle again out here, okay? So those are not as common as the third type that we see here. The third type, this is the one again that we probably picture when someone says Venn diagrams. We have what we call overlapping sets. Usually our sets are going to have something in common. So they have some elements in common, but then they also have some elements that are distinct. So some elements that only belong to their circle, but some that belong to both circles. So this time our universal set represents all of the vehicles in the world. So put all vehicles in the box. And some of those vehicles could be Fords, and some of those vehicles could be trucks. And hopefully you see how those could overlap. So over here we have Fords, and over here we have trucks. Okay, these two sets have some overlap. There are some Fords that are trucks and some that aren't, and we have some trucks that are Fords and some that aren't. So in the middle, in the middle here, the overlap, this section right here, that would be elements in common to both sets. So in that middle section, we would put something that is a Ford and a truck at the same time. So what's an example of something that is a Ford and a truck? Maybe like an F-150 could go in here. So an F-150 is a Ford and a truck. Now what's something that we could put in the truck circle that would not be part of the Ford circle? Like a Chevy Silverado, right? Chevy Silverado is a truck, but it's not a Ford. Or what's something that's a Ford that isn't a truck? Maybe something like a Mustang. Okay, Mustang is a Ford, but not a truck. And then outside of the two circles would be something that is a vehicle that isn't a Ford or a truck. Maybe like a Honda Accord. Right? A Honda Accord isn't a Ford, it isn't a truck, but it's definitely a vehicle. Okay? So we have disjoint sets with nothing in common, proper subsets where an entire set is in another, and then we have the common overlapping sets where we have some elements in common. Okay, now no matter the relationship, there are three what we call set operations that we should be able to perform when we're looking at multiple sets in one rectangle or one universal set. The first one we call the complement of a set. So the complement of a set represents all of the elements that are not in a set. Seems a little counterintuitive, maybe? What are the elements that are not in the set? But if you think about it, it does make sense to use the word complement. So maybe you think, I don't know if any of you are married, but like a husband and wife or a couple, they complement one another, where sometimes you call your significant other your better half. Maybe they have qualities or attributes that you don't. So together, you get all the good stuff. So you complement one another, and that your significant other makes up for what you lack. Okay, so that's sort of what's happening here with a set and its complement. So you have a universal set which contains everything, right? And then you have set A, which has some of the elements, and then you have the complement, which would be everything else. And together, the set and its complement make up the whole universal set. Okay? So the notation, and we'll get some examples on the paper here, just give me a sec. The notation for the complement of a set is what can look a little weird. There are three different ways that we can say the complement of a set. Let's say it's set A. So the complement of set A could be like this. A with it'll look like a little exponent of C. Or we could see A with a little prime notation. Or we could say we could see A with a bar over it. All three of those would be read as the complement of A, or A's complement. Okay? So again, if I want the complement of A, I want to know what's not in A, right? But in the universal set. So, for example, on number 1 here, the universal set is the numbers 1 through 5, 1, 2, 3, 4, and 5. If set A is the numbers 1, 2, and 3, its complement is going to be everything else. Everything else that's in the universal set but isn't in A. So the entire picture here is 1 through 5. If 1, 2, and 3 are here, what's left? Well, 4 and 5 are the only things that are in the universal set that didn't make it into A. So we have, now I just put markings all over my paper, the complement, goodness, Okay, so we said that A is 1, 2, and 3, that the complement of again, A prime, well, let's use A prime since they used it here. The complement of A would be what's not in A, but in the universal set. So what's left over would be 4 and 5. And what should happen every time is, again, a set and its complement should make up the entire universal set. So if you were to combine A and A prime, if you were to put together the elements from A and the elements from A prime, what you get is the universal set. So A and A prime together make up the universal set. All 1, 2, 3, 4, and 5. Okay? So together, a set and its complement make up the universal set. Let me put that over here. Oops, I took too much. Undo. This is my little moving tool. Okay, so a set and its complement always will together make up the universal set. And alright, how about the next one? A little less concrete. So let's say the universal set is all of the food in the world, and then a subset of that is fruit. What would be the complement of A? So if you put all the food in the world in a box, right, and one circle represents the fruits, what would be outside of the circle but still in the box? Well, all the food that isn't fruit, okay? So if A is fruit, A's complement is food that isn't fruit. And together, if you added up the fruits with the food that isn't fruits, what would you get? All of the fruit. Okay? So together that set and its complement make up the universal set. Okay, so here's a third example where we're using a picture. So let's look at our picture here. It says find the complement of A using the picture. So A, gotta be careful. Sometimes we might only see 15 and 21 as being an A, but A is this entire circle. So what elements are included? There's the 15, the 21, and the 7. So A's complement is what elements are still in the picture that are not in A. What's not in A? Well, not in A would be everything else, right? 5, 9, 12, 3, and 11. And together, the green and the pink, what's in A and what's not in A, make up the entire universal set. So we're going to say the complement of A. Well, let's put it all down here. So A contains 15, 21, and 7. And the complement of A contains the rest, right? Everything else. Everything that's not in A is the 5, 9, 12, 3, and 11. And then again, together, that's the universal set. Okay? Everything together. So you got A and then what's not in A as its complement. Alright, hopefully that's coming together for you. Alright, let's see. There's 2 more operations that we should be able to, so what we call set operations, we should be able to perform given some sets. So we can find the complement of a set. The intersection of sets is another operation. The intersection of sets, when we're looking for the intersection of sets, what we're trying to find are the sets that are in common to both A and B. So when I say what is the intersection of sets A and B, I want to know what elements are in sets A and B at the same time. So the intersection is what do the sets have in common? What is in A and in B? So think of it as the overlap in the picture, okay, or the shared elements. And we have a notation for this. So the complement of A is A with the prime notation, or A with the little exponent of C, or A with the bar over it. For the intersection, you can see the symbol here. It looks like an upside down U. So the notation for the intersection for A and B would be A intersected with B. That's how we could read that. Or you could also say the intersection, read the middle first, of A and B. Okay? So let's look at some examples. Let's try to find some intersections. What elements are in A and B at the same time, or what elements do the sets have in common? So A has the numbers 1 through 5, B has the numbers 3 through 7. So what elements do they have in common? Well, I could see 3. Highlighter is a bit fat here. I could see that 3 is on both lists. I can see that 4 is on both lists, and I could see that 5 is on both lists. If those are the elements that are in A and in B, if those are the elements they have in common, those represent the intersection for A and B. So technically we could say A intersected with B contains the elements 3, 4, and 5. Okay? Now how about something without the math? If set A is the United States and set B is the states that begin with the letter A, then what do those two groups have in common? Okay, what do the two groups have in common? Well, they would be states that begin with the letter A. So we can say this two ways, right? States that begin with the letter A would all happen to also be in the United States. So this is a proper subset. So we could say that A intersected with B is, we can give a description. We could say, sorry, we don't need the braces for a description. We could just say it's states that begin with A. Or, if we wanted to try to roster that out, what else could we say here? Let's use above, just because I am limited on space. The intersection for A and B is the roster of, what are the states that begin with A? That are also, right, happen to be the United States. So I know we have Arizona, get put on the list. Let's see, Alaska. Arkansas, Alabama, and I am in my head scanning a map of the United States. I think that's it. Okay, hopefully I didn't miss anything, but you get the idea even if I did. Okay, if that was I wouldn't put something that obscure in an assignment, but there it is. All right, let's look at example 3. So example 3, we have a picture of a Venn diagram. So we want to find the intersection for A and B. That is, what elements are in A and B at the same time. So these are the elements that are in A, right? 10, 11, 12, 15, 16. And then the elements that are in B are 15, 16, 21, 22, 23. So what elements are in both of those sets happen to be the elements that are in the overlap. So in the picture, it's really easy to see what A and B have in common. So we want to think of that intersection again as the overlap. So the intersection is the overlap. So the intersection for A and B here, A intersected with B, contains the elements 15 and 16. Okay? So that is the intersection again. It's what do the sets have in common? What is in one and the other at the same time? And the third operation is what we call the union of sets. So the union of sets unites sets or combines sets. So if I said find the elements that are in the union of sets A and B, then that means the elements could be in one set or they could be in the other. We would just combine them all. So this answers the question, what elements are in sets A or in set B? So the union of the sets, again, it unites or combines all the elements of the sets. And the notation is a U, which is a little confusing. You can see it here, right? Because we use the U for the universal set as well. But when you see it between sets like A and B, then that represents the union. So the notation for the union of sets A and B would be A united with B, would look like that. Or again, we could read it from the middle. We could say the union of A and B, or A united with B. Okay, those are the two ways to read that. So let's look at example 1. If I wanted to let's see, A is the numbers 1 through 5 again, B is 3 through 7. If I wanted to find the union, A united with B, what is in the union of those sets? Well, that means I have to combine them all. That means the elements could be in A or in B. So if I put all of these numbers together with all of these, if I combine them all, then A united with B would include everything from A, 1, 2, 3, 4, and 5, as well as everything from B. 3, 4, and 5, we've already got them down, don't have to repeat them, but then we have to tack on here 6 and 7. So if I united those two, put them all together, I would get the numbers 1 through 7. Okay? Picture example here. So if I said to find the union for A with B, if I said A united with B, that means elements could be in A or in B. Then the elements that are in A would be here, and the elements that are in B would be here. Now I don't want to know what do they have in common, that's C and D. I want to know if I united or combined all of those elements, what would I get? Well, I would get everything from this whole clump of circles, right? The only elements that are not in the union, right, are these guys. The G and the H, those are the only two that aren't in A or in B. So when I unite A with B, the only thing I'm going to exclude would be G and H. Okay, G and H are the only guys that aren't included there. So A united with B is going to include A, B, C, D, E, and F. The only thing we exclude would be G and H. Those are the only elements that aren't in either one of those sets. Okay? So those are the three operations. Now we're going to try to make a Venn diagram given some sets and then perform each of these operations one more time. So putting it all together here. Let's try to make a Venn diagram for the universal set here that includes the numbers 1 through 10. Set A has the evens 2, 4, 6, and 8. Set B has the numbers 1 through 5. So just as a rule, and we'll get more practice with this later, when you're creating a Venn diagram for some sets, you want to start in the middle of the picture. Okay, I want to try to fill in this region first. That means let's start with what do A and B have in common? Do you see any elements that are in common to A and B? Well, 2 is in both groups, and 4 is in both groups, which means I'm going to put 2 and 4 in the middle here. Now once I've placed those numbers, I'm going to get rid of them from my list. So 2, 4, done, taken care of. Let me get rid of them on the universal as well. Okay? Now what's left over in A has to go in the other part of the A circle. So in this region here, what's left over in A, I'm going to put here what's left over in A, 6, 8, and 10. So 6, 8, and 10 can go here. And then what's left over in B? What's left over in B? That's going to go in this B section. Okay, and left over in B would be 1, 3, and 5. So I'm going to put in 1, 3, and 5. Okay, now let me go back to my universal list. I just put in 1, 3, and 5, so I'm going to cross that off. And then in the yellow section there in A, I put in 6, 8, and 10. So those are the elements that are in A or B. Now the only thing left in the universal set is 7 and 9. And since 7 and 9 don't belong to A or B, then we're going to put 7 and 9 outside of the circles, but in the universal set. Okay? So now we have our picture. Hopefully that wasn't too terrible. Now let's try to perform the operations. So number 1 says to find the complement of A. So remember, we can look at the picture or we can look at our lists. A includes the evens, 2, 4, 6, 8, and 10. So what's not in A would be the rest of the numbers, right? What's not in A would be, I hate to undo my picture here, but so you can, that's not what I wanted to do. So that you can see one at a time with these questions. Let me try to help you here. Okay, what's not in A? So A includes the evens, 2, 4, 6, 8, and 10. What's not in A would be 1, 3, 5, 7, and 9. Those are the elements not in A. So this is going to be 1, 3, 5, 7, and 9. And together, those evens and those odds make up the entire universal set. Okay? Oh, man. Let me do this again. I had to get rid of my highlights for the next one, but didn't want to get rid of that. 1, 3, 5, 7, and 9. Okay. How about the complement of B? So B, again, let me just piece this out for you here. In B, we've got 1, 2, 3, 4, and 5. So what's not in B would be 6, 8, 10, 7, and 9. Okay, 6, 8, 10, 7, and 9. So not in B. B has 1, 2, 3, 4, and 5, 6, 8, 10, 7, and 9, or if you really want it to be in order, 6, 7, 8, 9, and 10. Although, if you didn't put it in order, it wouldn't matter. So, or, just so you can see it, we could have said 6, 8, 10, 7, and 9. It really depends if you're looking at the picture and not wanting to think about the order. It's totally fine to have it out of order. Okay? What do we got next? Number 3 says what is in the intersection. So this is the intersection. That means what do they have in common? What is in both A and in B at the same time? So the intersection, this is the overlap. That is this area here. So what's in A and B at the same time would be 2 and 4. So this is going to be elements 2 and 4. Okay? How about A united with B? So A united with B means we're going to combine everything from A or B. So everything from A or B, it means everything in those circles is going to be included. The only thing we don't count would be the 7 and the 9 because they're not in A or in B. So everything but 7 and 9. So everything but 7 and 9 means here we're going to have 1, 2, 3, 4, 5, 6, not 7, but we can put 8 there, not 9, but we can put 10 there. Everything but 7 and 9. Okay? Now these last two are a little trickier because you'll notice we've got 2 operations. So this says to take the complement of A and find the intersection with that and B. Now, if there's multiple operations, I would do this in multiple steps. So we're looking for an intersection of 2 things. Let me figure out what those 2 things are first, okay? So first, let's list out what's in the complement of A. So remember, A is 2, 4, 6, 8, and 10. So the complement was the odds, okay? You with me? Complement is the odds. So in the complement of A, I got 1, 3, 5, 7, and 9. That's that complement. And then what do I have going on in B? So in B, I have 1, 2, 3, 4, and 5. So in B, I have 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So this is saying, find the intersection of those 2 groups. What do those 2 groups have in common? What is the same on both of the lists? Well, let's highlight here. 1 is on both of the lists, 3 is on both of the lists, and 5 is on both of those lists. So those would be the elements in their intersection. So this final answer, the intersection for A's complement and B, is going to include 1, 3, and 5. Okay? All right, last one. Again, 2 operations, but this time we've got parentheses. And just like in any other math you've done, you're following a general order of operations. Parentheses, what happens in there has to happen first. That still applies. So we have got a complement of a union. We have to figure out what's in that union first and then deal with the complement. Okay? So the union for A with B, if I unite A with B, that means what's in A or in B. That means combine all the elements from A or B. And we did that earlier. Remember, that was everything except for 7 and 9. So in this union, I have 1, 2, 3, 4, 5, 6, not 7. I've got 8, not 9, but I've got 10. So I want the complement of that. Okay? So what's the complement of that union? What's not in that union? The 7 and the 9 are the only thing missing. So the complement of the union, and we could see it really easily on the picture, right? Here's our union. What's not in that union? 7 and 9. And that's going to be our answer for this guy. What is not in that union is 7 and 9. Okay? And we're going to get some more practice with those. In the next lesson, we'll throw in some Venn diagrams and relationships with 3 sets. And those set operations can get pretty complicated, but one step at a time, we should be okay. So work through the practice, and as always, if you find yourself struggling, you need some help, just reach out. I'm here for you. All right, guys, take care.